Good afternoon from Brussels. My name is Alex Martin, and I'm the head of GLOBSEC Brussels office. I am pleased to introduce the second to last session of GLOBSEC 2020 Digital Stage. We tried for the past days to bring to your attention the most relevant, interesting, and actual topics. But we decided to go one step further and bring to this conference a topic which is literally out of our COVID world. This is the future of Mars exploration. So let's go to Mars. And we are pleased to have with us Dr. Anita Sengupta, who is an aerospace engineer, entrepreneur, instrument-rated pilot, rocket scientist, and veteran of the space program. She has developed technologies that have enabled the exploration of deep space and novel transportation systems for over 20 years at NASA, Virgin, and Boeing. She's a research professor in astronautics at the University of Southern California and a founding member of 2 electric aviation companies. Dr. Sengupta will deliver a presentation for the next 20 minutes, and then we will have the opportunity to get a Q&A chat to get answers also to our questions. So Anita, the floor is yours.
Good evening, everyone from Los Angeles, and thank you for having me, Alex, at your wonderful conference. So today I'm going to speak about the future of Mars exploration with a focus on what has been done to date and where we're headed as a species as we travel towards the red planet. My name is Anita Sengupta, and I am an aerospace engineer and professor by training. So we can go to the next slide. Just to give you a little bit of background, we can go to the second slide, which says Engineering the Future. Hopefully it's up. So to give you a little bit of background about me, I spent the majority of my career working for NASA, which is the US Space Agency, developing technologies to facilitate the exploration of space. And about 15 years ago, I had an opportunity to work on this amazing mission to Mars called the Mars Science Laboratory Curiosity mission, which was going to send something the size of the car to the surface of Mars. And I developed an expertise on how to land spacecraft on the surface of other planets with atmospheres. And ironically, that's a class that I now teach at my university. So the talk of my today is going to be going through some of my lessons learned and some of the challenges that we have as a space agencies from around the world to accomplish Mars exploration going forward. If we go to the next slide will show you a video of some of the challenges associated with landing something on the surface of Mars. You can play the video now.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun, 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
A parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it will only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage, it's in a collision course with the rover. We must cut the bridle immediately and fly the descent stage away to a safe distance from the rover.
Okay, you can go to the next slide. Well, that was really exciting, and although it looks like science fiction, that is science fact. We designed that system that successfully landed the Mars Science Laboratory Curiosity rover on the surface of Mars, and that same entry system design will be used to land the Mars 2020 Perseverance rover on the surface of Mars. But to go back to the ultimate question is, why are we so interested in exploring Mars? And ultimately, the reason why space agencies around the world explore other planets and other asteroids and other comets and other places in the universe is to understand our place in the universe. And a great example of that is really close to home. In this image, you can see our home planet Earth in the middle. You can see Venus off to the left and Mars off to the right. And what's so interesting is that when the solar system first formed, these planets were very similar to each other in terms of having water on the surface and an appreciable atmosphere. But over the course of the past multiple billions of years, the planets have evolved quite differently. Earth, of course, is our home. It's beautiful and wonderful and has water and air that we can breathe, but Mars has a very thin atmosphere, a very cold temperature, and Venus has a very hot temperature and very high surface pressure. So what we can see is that climate change is a planetary phenomenon. We can see that with our own neighboring planets, Mars and Venus. So we can go to the next slide. So why are we so interested specifically in Mars? Well, there's two reasons. One is the planet is somewhat fascinating. It has interesting evidence of prior geologic activity. For example, Olympus Mons, in the image on the upper left, is an extinct volcano about 6 times as high as Mount Everest. Valles Marineris, which is the image on the bottom, is sort of the Mars's version of the Grand Canyon, but once again, also significantly higher. And we can see that the volcanic activity has shifted and changed over the course of time. And that might be responsible for the reason why the planet changed in terms of its atmosphere and water flowing on the surface. And one of the theories associated with that is that there was a large celestial body which impacted, which then disrupted the magnetic field and ripped away the atmosphere. And the reasons why we send spacecraft there is to take scientific measurements to understand how the planet has evolved the way it has. The second reason, of course, though, is for future human exploration to the surface of the planet. And when we develop technologies for robotic exploration, and when we collect scientific data about the planet using robotic exploration, we set the stage for future human exploration. So those are the two reasons why we explore Mars. We can go to the next slide. So one of the things that's really important for human beings and for life in general is the presence of water, so that we can use it to be able to survive and so that life could have ever existed in the past. And what we've discovered with robotic exploration over the past 20 years of Mars is that there is actually flowing water on Mars. It's not big, heavy water flows. It's more like a wet mud, which you can see in these images here. So you can imagine the first human explorers, when they go to the planet, would like to tap into these potential sources of subsurface aquifers to be able to grow food and plants and drink water themselves and potentially produce oxygen using that material. And all of this data exists because of the robotic exploration of space, which is facilitated by agencies such as NASA, ESA, JAXA, and ISRO. We can go to the next slide now. And so one of the really important parts of space exploration is the development of new technologies to facilitate our understanding and our ability to get there and to move around and have mobility solutions on the surface of the planet. So since the 1970s, we have been sending rovers to the surface of Mars. We've done it a total of, or rovers and landers, we've done it a total of 8 times now. And what you can see in this image is that each time we send another vehicle to the surface of Mars, we increase its size, we increase its complexity. So by learning on the past, we build the future, and we evolve our technology to be able to do more science and eventually send people to the surface of the planet. And so the picture of the rover that you can see on the right is the Mars Science Laboratory Curiosity rover, which is essentially the same rover in terms of size and capability as the Perseverance rover. Perseverance has a slightly different mission and a slightly different set of instruments, which I will discuss next. So we can go to the next slide. So the purpose of the Perseverance mission is to essentially conduct astrobiology research to determine whether or not Mars once supported life, whether or not it was habitable. And it does that through a series of instruments, specifically looking for something called a biosignature. And a biosignature is sort of a chemical fossil which tells you whether or not life could have potentially existed on the surface in the form of molecular compounds or in the form of certain types of isotopes. So when you think about the rover Perseverance, which is on its way to Mars right now, you can think of it as a robotic geologist, carrying a suite of instruments on its back to make these types of measurements. The secondary purpose for the Perseverance mission is to enable future human exploration. And it does that by, in one way, actually demonstrating something called in situ resource utilization, which allows you to take Martian carbon dioxide and convert it into oxygen. So showing that you can essentially live off of the land by using what is around if you're smart about it, which is what you would have to do when we go to Mars. And of course, the most fascinating feature of the Perseverance mission is that it's going to collect a sample. It's going to cache a sample, store it on the surface of Mars so that a future mission called Mars Sample Return will collect that sample, send it back to Earth, and with Earth-based laboratories, understand even better the potential for life to have existed on the surface of the planet. So we can go to the next slide now. So where is the Perseverance rover going? It's going to a location called Jezero Crater. And the reason why NASA and the science community chose Jezero Crater is because this area was once flooded with water many billions of years ago in an ancient river delta. And when you look to environments which are wet on Earth, you obviously find evidence of lots of life. So if you go to an environment which was once wet on the surface of Mars, you could potentially find evidence of prior life that existed on the surface. And the hope, of course, is that we can find evidence of prior microbial life on the surface of Mars in the past, and perhaps, even in the present. But that's something that we will have to uncover when we eventually send back that cache sample to Earth and conduct more detailed scientific measurements with Earth-based laboratories. But the image on the left here is showing you the different vehicles that we have sent to the surface of Mars over the course of the past 20, 30 years, and where the Mars 2020 Perseverance rover is located in Jezero Crater in that river delta from the past. So we can go to the next slide. So this coming up here is a video of the entry, descent, and landing process. You can start the video now if you're able to. So the real challenge of landing something on Mars is that you have all of this energy, all of this speed. You're coming in at a speed of 20,000 kilometers per hour, which is basically 30 times faster than a commercial airplane. So over a period of 7 minutes, you have to slow that vehicle down to land the payload or the rover or eventually people safely on the surface of the planet. And you do that with a series of technologies. One of them is called the heat shield, which takes you to about 2 times the speed of sound. Then you deploy a very large parachute, which takes you to around 300 kilometers per hour. And then finally, you descend to the surface on a series of rocket motors or engines, which help you slow further down to touch down softly on the surface of the planet. So this sequence that you see here was successfully completed by the Curiosity rover back in 2012, and it's the same sequence that the Mars Perseverance rover will use in just a few months' time. Very complicated, very difficult, because the rover has to execute this maneuver autonomously by itself with no help from the ground, because it's impossible due to the time delay of the speed of light. And so that is the landing sequence that Mars Perseverance will use in just a few months' time with a few updated additions. So we can go to the next slide and cut past this video if you're able to. So what I'd like to talk about next is a little bit about the science of the Mars Perseverance mission. So as I mentioned before, the rover is essentially a robotic geologist, which means that it carries a series of instruments on its back. And so by using a series of spectrometers, as well as cameras, as well as ways to determine what is in the composition of the atmosphere and the soil, the rover is able to make these scientific measurements. And one of the most important instruments, which is on board the Perseverance rover, is the MOXIE instrument, which basically allows the rover to create oxygen from Martian CO2. This is a key technology which will be needed for future human explorers so that they can survive safely on the surface of Mars. So Mars not only has a low temperature and a low pressure, its atmosphere is primarily carbon dioxide, which means that the crew would have to be able to convert CO2 into oxygen to be able to survive on the surface of the planet. So by taking a look at the geology, by taking a look at the atmosphere, by taking a look at the weather, more information can be determined about where we've landed, as well as about how interesting the samples are that we are going to be caching with this rover. So we can go to the next slide. So the way the rovers are named is actually with a naming competition before each mission. And so the winner here was Perseverance, which followed Curiosity. You can see the size of this rover. It's about the size of a small car. It has about the weight or the mass of a small car. And it has a series of 6 wheels which allow it to climb over very large surface features safely without tipping over or without getting damaged. Of course, the gravity on Mars is less than what you would have here on Earth, but it's still very challenging to be able to climb around. It does this quite slowly because it doesn't need to do it quickly as it's collecting scientific measurements along the way. And it also has a very unique power source called an RTG, a radioisotope thermoelectric generator, which means that it doesn't have to rely on solar radiation to generate power. It self-generates its own power, which allows it to keep itself warm and operate more hours of the day than you could do on solar power alone. Another unique advanced technology which was demonstrated by Curiosity and is being demonstrated again by the Perseverance mission. So we can go to the next slide. One of the new features of this mission, which I think is very exciting because I am an electric aviation entrepreneur, is that the rover is carrying a Mars helicopter, which is a single rotor counter-rotating system, which will allow it to do aerial reconnaissance in the vicinity of the rover once per day. This tiny little helicopter is powered off of a battery and solar panels to recharge its battery. It's capable of a 90-second flight, and it's able to go into the sky, collect images, which allows the rover to better understand its surroundings. It's incredibly lightweight, only 2 kilograms, and this is necessary because the atmosphere on Mars is very thin, which means it can only generate a very little bit of lift. So it has to be very lightweight to counteract the fact that the atmosphere is quite thin. This is the first time an electric aircraft is ever being flown on the surface of another planet, and I think this is very exciting, and it's an important technology demonstration asset that could be used on future missions to other planets that also have atmospheres. And it is called Ingenuity, aptly. So we can go to the next slide now. So the countdown to Mars. So where are we today? Well, the rover successfully launched at the end of July, and now it's on its way to the red planet. It's targeted to land on February 18th, 2021, where it will execute its entry, descent, and landing sequence that I showed you in that video before. After it safely lands, a few minutes later, it will check out its systems, and then it will begin its surface mission, its surface journey, to collect those scientific measurements for a minimum of 2 Earth years, which is the minimum set of data that it will collect. It'll likely rove around the surface for many, many years after that. So we can go to the next slide. So what is the future of Mars exploration? We can now go to the next slide. So the future of Mars exploration is to set up for human exploration of Mars. And so there are many technologies that have to be developed for a colony, no matter how small, to successfully survive on the surface. And a lot of that is surrounded by the principles of in situ resource utilization, which is living off of the land, which is being sustainable, which is something that we need to do here on Earth first successfully to combat climate change. And we can leverage all of those lessons learned into how human beings would live on the surface of another world. So when we talk about sustainability for surface missions on extraterrestrial locations, we're talking about power generation from the sun. We're talking about radiation protection using the Martian environment and soil to mitigate some of those high energy particles, the production of water by tapping into those subsurface aquifers, and then the creation of rocket fuel, and then also plants called extremophiles using Martian CO2 to grow those plants. So to wrap things up, we can go to the next slides, which is when are we going to see the first human beings on Mars? You can go to the next slide if you're able to. Probably within the next 15 to 20 years is my guess. It is going to require international collaboration and a lot of funding, but I do think that we'll get there. This is an image of probably what the first colony would look like. And then the very final slide, you can go to the last slide. The question that I'll leave you with as an audience is that would you want to live on Mars? Would you want your children to live on Mars? Do you see us as a society actually living on the surface of Mars? So thank you very much. And now we'll do a short Q&A.
Thank you very much, Anita. This has been absolutely fascinating, and not just for me, I'm sure also for our audience. And I want to pick up where you actually left. And you talk about humans to Mars in about 15 or 20 years. So there is talk about a human mission to the moon. Do you think that another moon-landed mission is needed before we get the humans on Mars?
So there's 2 different aspects to space exploration when human beings are involved. One is the development of the technologies to be able to accomplish it, and the other is the ability to be able to survive off Earth in these sort of sustainable ways for a long period of time. So because the moon doesn't have an atmosphere, a lot of the technologies that are developed for a moon landing are quite different than the technologies that are developed for a Mars landing. So for example, you can't use a parachute on a moon because there's no atmosphere. You pretty much would just use retro rockets. But that being said, the idea of being able to live sustainably, to be able to live for an extended period of time in a high radiation environment is something that we'll learn a lot about with a future human mission to the moon.
Fantastic. I do want to have a short disclaimer saying that you were actually responsible for the supersonic parachute that helped Curiosity land on Mars, and it's important for everyone to know that you are the mastermind behind the technology of slowing down from over 20,000 kilometers an hour to 0 to put the rover successfully on the red planet. So you mentioned that in 15, 20 years, we will be able maybe to go there. But meanwhile, the Mars 2020 mission is on its way with a planned date of 21 for landing. And the European Space Agency is also planning to send a rover in 2022. So how can space agencies can better pool resources together to make this even more cheaper or even more effective?
Well, so first I will say it's absolutely essential to support human exploration for space agencies to pool their resources, because when you look at the cost associated with robotic missions, when you look at the cost associated with human missions, you're looking at an order of magnitude, if not 2 orders of magnitude more cost. So it's simply impossible for one country to be able to do this alone. You have to do it with space agencies from around the world. So there's several ways to do that. You could choose to break it up into a pie where one country takes responsibility for the launch vehicle, another takes responsibility for scientific instruments, another takes responsibility for the spacecraft, and that way you share the costs. Or you can do it in a more holistic fashion where you look for who has the expertise that we need and you form an international team who works on everything together. And I definitely would be a supporter of the latter because I think that's super exciting as an engineer to be able to work with space agencies around the world.
We'll make sure that at least this part of our conversation will be sent to multiple space agencies around the world. But still, the issue of space exploration is not only a matter of international cooperation, but also of a space race, and that's where geopolitical tensions come into place. So what are your thoughts about this issue? Is the Mars exploration, will it lead to more international cooperation or to more geopolitical tensions?
So I think there's another aspect of it, which is it leads to competition, and competition can actually lead to efficiencies, new technologies, innovation, which ultimately facilitate the exploration of space. And a great example of that, which is completely in line with our discussion, is the Commercial Crew Program that NASA engaged in, which now is sending astronauts to this International Space Station. So the Commercial Crew Program came in at a very low development cost, only a few $1 billion, yet it gives us access to the International Space Station, which will save the U.S. Space Agency money. It will facilitate space tourism. So I would see this aspect of competition amongst countries, amongst private companies, as actually reducing costs and finding new efficiencies and new innovation.
And talking about this competition, we have a question from the audience, from Katarina Shverdnerova, asking if you could compare the goals and technological level of the American, UAE, and Chinese Mars missions and their significance for the future of space exploration.
Well, I'll be honest to say that I don't know enough about the details of their mission from an engineering perspective to be able to compare it. But I would say that because they're scientific missions and they have scientific objectives, they're probably following the same objectives, which is to understand past habitability, whether or not there could have been microbial life on the surface, whether there still is today. And to be able to do those types of measurements, you have to develop instruments, you have to have telecommunications ability, you have to have power on board, you have to have a spacecraft bus that can do those things. So I think it's great that we're creating different sources of this expertise across the globe, because that immediately feeds forward into this vision of a global or planetary Earth human exploration program that I hope happens in the next 15 to 20 years.
You mentioned climate change and sustainability and the idea of protection of the outer space in your presentation. So this is a very important, the planetary protection is an important aspect of sending spacecraft to Mars. So will it be maintained once the first humans will get there?
So that's a really good and important debate that we need to have. So just as a little bit of background, when we send a spacecraft to a planetary body, a celestial body, which may have life, we use planetary protection protocols to make sure that we don't bring Earth bacteria or Earth viruses to this planetary body and therefore damage whatever might be there in terms of, microbial life, or even contaminate our own scientific measurements. So when we send rovers to the surface of Mars, we engage in a variety of protocols which make sure the rover's clean so that we don't bring our Earth-based bacteria to the surface of Mars. Of course, when we send people, it's going to be a very different situation because people inherently have a microbiome inside them and they have bacteria that we use to survive. So we will be bringing bacteria from Earth to Mars. So we need to have a global conversation. We need to have a policy discussion as to how much is okay, what are we going to do in terms of to reduce our footprint where we're actually creating this human microbiome environment. These are conversations that have to be had at that geopolitical level, which involves scientists and engineers as well as politicians to say what is the right way to handle this. But it's something that we're going to have to broach very soon.
Dr. Sengupta, this has been really, really fascinating and a great pleasure to have you with us today. I would like to thank you very much for joining the digital stage of GLOBSEC. And as I wrap up this panel, I would like to invite you all to stay online for the last panel of GLOBSEC 2020 digital stage. And that's an update on Belarus with Svetlana Tsikhanouskaya, moderated by Terry Martin of Deutsche Welle. Thank you.
Thank you.